Hi there, here comes another one. Okay, this one's going to be a standing wave problem. So it's a problem involving a standing wave on a string. So a string stretched across a distance of 1.2 meters has a fundamental frequency of 190 hertz. And we want to calculate a couple of different things here. First of all, we want to know what is the speed of waves on this string. And second, by what percent will we have to increase the tension in order for the fundamental frequency to be 200 hertz. All right, so let's get started. Okay. Let's see. First of all, speed of waves on a string. Well, there's a couple things that we know about this. First of all, we know that v is equal to f times lambda. Okay. We also know, and that's true of waves in general, so, whether we're talking sound waves or later in the semester light waves, or for now waves on a string or whatever. We also know specifically for waves on a string that v is equal to the square root of the tension divided by the linear density. Okay? This last one is not going to be too much help to us right now because we don't have a lot of information on this. We do have information about things like frequency, and this 1.2 meters, that's the length of the string, that's going to be related to the wavelength. So we're going to do it this way. Okay, so we'll actually end up using this for part B, but for now we're going to do it this way. So our frequency, and notice this is the fundamental frequency, and so that means the frequency of the first harmonic. Okay, so let's see, the frequency then of the first harmonic is equal to 190 hertz. Okay, in general, the wavelength for standing waves on a string, okay, is given by lambda n is equal to 2L divided by n. All right, so this gives you the wavelength of the nth harmonic. Now, if we want to use this formula, we have to make sure that the frequency and the wavelength we're talking about are for the same wave. So since the frequency I know about here is the first harmonic, that means I'm going to use the wavelength of the first harmonic as well. So lambda 1 equals 2L over 1, which is 2 times 1.2 meters. And that's 2.4 meters. So that's the wavelength of our fundamental harmonic, and our frequency is that. So now I can say V is equal to 190 hertz times 2.4 meters. And when we work that out, we end up with 456 meters per second. Okay? And so that's the speed of waves on this string. All right. Let's see. Part B. By what percent will we have to increase the tension in order for the fundamental frequency to be 200 hertz? Okay? So the frequency, as we set up here, is equal to V over lambda. And the way this is related to tension is that V is the square root of F over mu. Okay? The tension in the string divided by the linear density. Now, let's see. I don't have a lot of this information. I don't have, what the tension is. Okay, I'm interested in how much it increases by. I don't have any information about the linear density. I do know the wavelength, but basically that's not going to help me. But what I can do is I can take a ratio here. In other words, there are two different frequencies that I'm interested in at two different tensions. Okay? And so when you've got a situation where like here, we know one frequency and we know the other frequency, and we're interested not in the tension itself but in the ratios. That tells us we might be interested in taking a ratio here. So F2 over F1 equals square root of F over mu divided by lambda F1 because I'm changing I'm sorry, F2 here because I'm going to be changing the tension in a little bit, so that's going to change, divided by the square root of F1 over mu divided by lambda. Okay? And a bunch of this stuff is going to cancel. The lambdas are going to cancel out. I got a square root of mu up here and a square root of mu down here that cancels out. And so this leaves me with F2 over F1 is equal to the square root of tension 2 divided by tension 1. So let's see, this is 200 hertz divided by 190 hertz equals the square root of F2 over F1. If I square both sides of this, I get F2 over F1. When I take this ratio and I square it, I get 1.11. So F2 is equal to 1.11 times F1. Okay? Now, let's see, what were we trying to do here? Okay, we were trying to figure out by what percent the tension is going to increase as we do this. Okay? And so, basically, this 1.11, this part here, tells us that it increases by 11%. Okay? In other words, if this had been 1.5 times F1, then we'd have said it increased by 50%. Okay, if it was 1.2 times F1, we would have said 20%. It's 1.11, so that means that the tension increases by 11%. That's it.